Get some practice with finding and classifying relative extrema. I will go ahead and get caught up on my first partial derivatives at least. Maybe measuring right, sorry. Are my first partial derivatives matching what you've got? So one of the things to note here, when we set these equal to 0, conveniently, that top one factors, and that's really our fastest path forward through the algebra part. So the top one factors, and I can pull out a 6x, and then I'm left with 2 minus y if I do that, which means that solutions to my partial with respect to x look like x equals 0 or y equals 2. One thing to note, 0, 2 is not a critical point. Or it might be, but I don't know that it is yet. And the reason for that is both of these are solutions to my partial with respect to x being equal to 0. But in order to be a critical point, I also need that partial with respect to y to be 0. So factoring it now means I can kind of play out the scenario, what if x is equal to 0? And then play out the scenario, what if y is equal to 2? So if I play out x equals 0, down here in my partial with respect to y, then this becomes 12y minus 3y squared is equal to 0. And that, I can now pull out a 3y and have 4 minus y is 0. That has now given me 2 critical points. X could be 0, y could be 0 for matching up with the 3y part, or x could be 0 and y could be 4. Then I can play out the scenario, what if y was equal to 2? And if y were equal to 2, and I look at my partial with respect to y, 2 times 12, so that's 24, minus 3x squared, minus 2 squared is 4, 4 times 3 is 12. So now I've got that would be equal to 0. So 12 minus 3x squared is 0. I can pull out a 3. I'm going to be left with 4 minus x squared, which means this is giving me 2 critical points. X could be positive 2 while y is positive 2, or x could be negative 2 while y is positive 2. So now I've got 4 possible critical points to play with. So if I construct my matrix of second derivatives, I think I can squeeze it in and keep it on screen. So if I build my matrix of second partial derivatives, if I start with fx and I take the derivative with respect to x a second time, I've got 12 minus 6y. If I take that derivative, but now with respect to y, I've got negative 6x. If I start with my partial with respect to y, I take the derivative a second time, but with respect to x, I get negative 6x, which is good. We should match. And now if I take my partial with respect to x, I get negative 6, sorry, with respect to y. Cool, I got this. With respect to y, I'm going to have 12 minus 6y. I want to point out that it is a Not exactly a coincidence. I chose the problem, so it's not really a coincidence. But in general, these partial derivatives don't need to match up. It's just the mixed ones. It just so happens that I chose a function where the second partial with respect to x and the second partial with respect to y happen to be the same. So when we're at 0, 0, this would look like 12 times 12 minus 0 squared. That is definitely positive. And both of my second derivatives are positive, so I know that means we're concave up, and this is a relative min at 0, 0. Oh, we can plug in 0. If I plug in 0 for x and y, this one conveniently is 0. If we look at the Hessian at, where are my other points? Oops. So 0, 4. So if I look at 0, 4, when I plug in 4, 6 times 4 is 24. So 12 minus 24, I would have negative 12 times another negative 12 minus 0, because my x is still 0. This is positive. This time, both of those concavity pieces are negative, which means I'm concave down, and I've got a relative max at 0, 4, and if I plug that in to get the z value, f of 0, 4, I'm going to skip all my x pieces, so that's 6 times 4 squared minus 4 cubed. And then if we check our Hessian at our other two critical points, -2, +2. So this time when I look at my, oh, okay, so y is 0, 4, a relative maximum. Again, I'm not drawing the entire graph. I'm just looking at what's happening on the graph very, very near that critical point. These are both telling me about the concavity. So that's telling me that I'm concave down in the x direction, and I'm also concave down in the y direction. So very near that critical point, whatever else is happening, I know that I had to be at a relative maximum.
So positive, negative is not like when you multiple f x and f y, but like interest.
So right. So first we look at the overall Hessian, right, which is the determinant of this matrix. So I can either use the matrix or the formula. They're interchangeable, but we're looking at, so like first step is overall, does that overall formula give us a positive or a negative? And if that overall formula gives us a positive, then we need to look at the concavities. If the overall formula gives us a negative number, we already know we're at a saddle point. 2, 2. So when I plug in 2 for y, my fxx is 0 and my fyy is 0. So this is 0 times 0 minus, when I plug in -2 here, that'll become a positive 12 squared, and overall this is negative. So I know that I'm at a saddle. And this is what I was talking about when I said that extra piece on the end, looking at the mixed partial derivatives, that really comes into play when I'm very flat. So when my concavity in the x direction and my concavity in the y direction are both nearly 0, or in this case, actually 0, that's when this mixed partial derivative really influences the shape of the graph. One last one to do here, and our Hessian at 2, 2. Same thing's gonna happen on my fxx, fyy. This will be a -12 squared, but that's still gonna give me a value less than 0, and this is also a saddle. And again, if I were putting this into WebWork, it is important. WebWork is asking you for the point, which means you do have to plug it in and figure out what that Z value is.